are you ready?
Yes. Yes.
Okay, very good. So welcome everyone for this last session of the webinar Control in Time of Crisis for this year 2020-2021. Today we have the pleasure to listen to two talks. So the first one will be by Rodrigo R.Lecaros on stability estimate for the semi-discrete linearized Benjamin-Bona-Mahony equation. And so before we start, please, I would like to remind you to turn off your microphone during the talk, so that there will be no noise, no additional noise during the talk. Well, thank you all, and please, Rodrigo, it's up to you.
Okay, thank you, Silvan. Thank you to the organizer for the opportunity to give this talk. And thank you everybody for coming today at this presentation. Okay. First, this is a joint work with Jaime Ortega and Ariel Perez, both from the University of Chile. Ariel is finished his PhD, and this work is part of his PhD thesis. Okay, let me start. Let me talk to you about the BBM equation. Well, Benjamin-Bona-Mahony in 1972 proposed a model for the propagation of one-dimensional, unidirectional, small amplitude, long wave in nonlinear dispersive media. It is a dispersive equation, but has a different behavior of the classical dispersive equation, for example, the KDB, because, for example, his infinitesimal generator of the semigroup has a compact part here, and then has a different behavior. Let me tell you about the Leonard-Rossier and Zhang develop a unique continuation property for the BBM equation in a periodic domain. And in this year, Da Silva and Frey give an alternative proof using geometrical argument for the periodic case and for the case when the equation is considered in over all R. Zhang and Suasua consider a linearized BBM equation with a space-dependent potential. In this work, it was established that the only solution of the linearized BBM equation, such that U is 0 at both sides of the interval, is the trivial. Is the trivial provided that both alpha and beta do not vanish on the same open subset of the interval 0 to 1. In the case when alpha is equal -1 and beta equals 0, Sorin-Migu proved a unique continuation property with additional boundary condition, Ux in x equal 1 is 0. And he studied the controllability result for this equation. Well, Yamamoto in 2003 considered this BBM-like equation. Yamamoto considered this equation with coefficient P and Q, which depend of the time and space. And he proved that the only solution of this equation with null initial condition and which satisfies that the Dirichlet and Newman condition at one side of the domain are 0 is the trivial. This is his unique continuation property. He used a Kahneman inequality for the Laplacian operator with null Dirichlet boundary condition, and then he turned the Kahneman's parameters to infinity in order to absorb an error term which appeared when he used a cutoff function to fix the boundary condition to the hypothesis of the Kahneman's inequality under consideration. What is our objective is try to study the controllability, the unique continuation property for this system. Then we are interested whether a unique continuation property, as in the work of Yamamoto, still holds for a semi-discrete approximation in the space of the BBM equation. We recall that in general, the unique continuation property is not possible to obtain in an exact way for the discrete case. For instance, in the continuous setting, the classical result, if U is harmonic in a domain with U and the normal derivative of U in a part of the boundary are B0, then U is equal to 0 in a full domain, does not hold in general for the discrete case. An explicit counterexample due to Otavio has been presented by Enrique Suazua in 2005 in this work. However, for this equation, it is possible to obtain a unique continuation property under restriction over the mesh size. Okay. Well, in order to avoid the difficulty related with the relation between the Carlemans parameter and the mesh size, we improve the presented by Yamamoto in the continuous case. We improve the proof presented by Yamamoto in the continuous case. We obtain this theorem, this stability theorem, for the solution of the BBM-like equation. And with this theorem, in this result, we can estimate the energy of the solution, the full energy of the solution, in terms of this right side, which is evaluated in x equal 1. Therefore, from this stability result is as a consequence of this stability estimate, we can obtain as a corollary the Yamamoto result. Because if we have U and derivatives respect to x of U in x equal 1 are B0, the full energy is 0, therefore the solution is 0. Of course, for obtaining this inequality, we need assume U, the initial condition is 0. Well, how we obtain this stability result in the continuous case? Well, is application of this Carleman inequality. This Carleman inequality is for the Laplacian. And then the proof of the previous stability estimate is a consequence of this Carleman inequality for the Laplacian operator. Yamamoto considered a Carleman inequality for a function with compact support. We consider this Carleman with boundary terms. That is the principal difference. How we obtain the stability result? Well, it's very simple. You consider the Carleman inequality, but we replace B equal UT, and from the BBM-like equation, we obtain the second derivative of V, and we replace in the Carleman estimate. Then we obtain this inequality. Now we need to absorb these red terms with this other side. And well, P and Q are B-bonded. Then, for example, absorb UT is not problem. We need to take S more, we need to consider S greater. But the problem is how we absorb UX and U. In that sense, we need a Poincare inequality in some sense, because we need to bond it U in terms of UT and UX in terms of UX UT. But this Poincare inequality, of course, is with a weight, because we need to consider the terms on front, which is the exponential of this phi function. For that Poincare inequality, we find this lemma, which is by Isakov. In this book, you can find this lemma, and this is actually the Poincare inequality, but with weight. Then using this, we conclude the proof of the stability, the previous stability estimate in the continuous case. Well, we have this unique continuation property for the semi-discrete BBM-like equation. Here, U is the solution of the discretization of the BBM-like equation, we assume that there exists a positive constant m, such that the normal of the function p and q are b-bounded by m. Then we obtain when we obtain this unique continuation property, which says that there exists H0 greater than 0, such that if the final two nodes of the solution are V0 for all time, then and of course the initial condition is 0, then the solution is completely 0. Then this result is the natural extension from the continuous case presented by Yamamoto. Okay. Well, before to present the ingredient of the proof, let me comment some reference about the discrete or semi-discrete systems. Several recent works have been concerned with the discrete and semi-discrete Karleman estimate for the second-order differential operator. The hyperbolic case has been developed for the one-dimensional case by Duvan and Hervedosa in 2013 to study the stability of an inverse problem to recover a potential term in a semi-discrete wave equation. The elliptic case has been developed by Frank Boyer et al. In 2010 for one-dimensional case to establish a relaxed observability estimate for the associated semi-discrete parabolic equation. And a semi-discrete Karleman estimate for parabolic operator have been established by Boyer and Le Rousseau in 2014 for multidimensional Cartesian grid. Moreover, in 2014, Nguyen studied in the one-dimensional setting a semi-discrete parabolic operator with discontinuous diffusion coefficient. Both of them obtain a relaxed controllability result for the presented system. And in this reference, Hervedosa and de Gournay studied the Laplacian operator in arbitrary dimensional to prove the stability for discrete Calderon problem. With limiting a Karleman weight function, the weight function is linear. In the aforementioned work, the discretization was based on finite differential scheme. Also, the Karleman parameter cannot be arbitrarily large, which is related to the discretization step size, in contrast to the continuous setting. Let's finally mention that recent article, where you can find a full discrete Karleman estimate for parabolic operator, have been obtained by Victor Hernandez Santamaria and Gonzalez Casanova, where the spatial and time discrete step size parameter are connected to the Karleman parameter. Finally, I want to comment this work by Sorin Miku, where he studied the 1D wave equation, semi-discrete 1D wave equation, but he didn't use a Karleman estimate. He used a spectral analysis. Well, the notation. The problem of the principal problem of this or the principal tools of this problem need a lot of notation. Now I want to introduce the notation of the mesh and the operator that will be used through this presentation and necessary to start our result. We introduce the following regular partition of the interval 0, 1. Here is our mesh. And we define the following dual mesh. For instance, for example, for W, a subset of M, we define W prime and W asterisk, where tau plus and tau minus of W are defined by this expression. That represents the motion of the point of the left and the right, but only the half of the distance between the points, the original mesh. With this, we can consider this definition. Here we have the interior of the mesh, and here we have the closure. Let me show you with a picture. First, we have here the set W. Here we have the original points, but we don't consider the extremest point. Here the x0 and xn, we don't consider this one. This is the ensemble, this is the interior mesh. Okay, the interior mesh is W. And W bar is the full original mesh. And here we can consider the dual mesh. What is the dual mesh? The dual mesh are the points that are between 2 points of the original mesh. That is y1, y2, y, this y are a point between 2 points of the original mesh. And the difference of the W prime and W asterisk is W prime is the dual mesh for the W, and W asterisk is the dual mesh for the W bar. For simplicity in the notation, we say Q is the W times 0t, and W prime and star, or excuse me, asterisk is the prime and asterisk of the mesh. And of course, the boundary reference to the boundary of the mesh. Well, with this different definition, of course, we can consider the boundary. The boundary in this case is very simple, are 2 points, 0, 1. And we can introduce the operators, the average operator and the difference operator. The average operator is simple, here U is a function defined over the original mesh. Okay, then we can evaluate U in the points of the original mesh. And this operator now define a function over the dual mesh. For that reason, when you take a point Y in the dual mesh, you can, in order to evaluate U in this dual mesh, you need to compose with tau plus or tau minus, which is motion, the point Y, h over 2 at the right or to the left, in order to evaluate U over the original mesh. In that sense, for example, if you want to know how is the average in Y1, you observe you need to consider U in Y1 plus or minus h over 2, then you have U evaluated in x1 and x2. For that reason, the average of the function in y1 is the average of the value of the function u in the point x1 and x2. Of course, it is the same for the difference. Well, of course, we can introduce the normal. Here is very simple. In x equal 1, the normal is 1. In x equals 0, it's minus 1. And of course, we can introduce, we need to introduce a trace operator because we need to consider boundary terms. And the trace operator is an operator which gives you the possibility to evaluate a function which is defined over the dual mesh, okay? But evaluated when you are in the boundary. Because when you are in the boundary, for example, in x equal 1 here, when the normal is 1, you need to evaluate a function which is defined over the dual mesh, then you need to move to the left. For that reason, you need to compose with tau minus. Or when you are in the x equals 0, you need to move to the right. For that reason, appear tau plus. This is a consequence of when you try to make an integration by part. Well, with this notation, we can now introduce our stability result for the semi-discrete BBM-like equation. This theorem gives you is more or less the same of the continuous case. The only situation here, you need to replace the derivatives with respect to x with this difference operator, dh. And here appear, of course, the average operator. Here, the boundary Q plus represents simple is x equal 1. This term is evaluated when x is equal 1. And here appear the trace operator because this term is necessary to evaluate in the dual match. The other principal difference with the continuous case is here appear a restriction the size of the parameter of the parameter S with respect to the H. Well, before to start with the sketch of the proof, let me show you how change the equation when we use the new notation. Well, this expression is possible to written in this form. Here we can see the 2 times we apply 2 times the derivative in order to replace the Laplacian. And here this derivative is actually the composed between the derivative with average operator. What is important to see here, in general, when we apply one of these operators, this new variable live in the dual match. But for that reason, we need, in all this term, we need the second order operators in order to this equation is well defined over the original match. For that reason, here appear 2 operators, here appear 2 operators. Well, let me show you some formulas related with these definitions. For example, the derivative, the discrete derivative of the product, we have this formula, which is more or less the rule, the chain rule, and the average of the product, the derivative of the square, which is the 2 times derivative of u by the average of u, the average of u squared. Here we have one inequality, and actually we can, for example, compute this is, I don't know, the Leibniz rule for with our operator. Well, integration, we need to define some integration in the discrete sense, and the integration over the boundary is simply evaluating the function on the boundary. And with this, we can compute this integration by part. Here there is a difference between the previous work. For example, we follow the ideas introduced by Herbedosa et al. In this notation, we don't make difference between the operator D applied over B, applied over a function of in the original match or in the dual match. We don't make a difference of the operator. But for that reason, we need to make a difference in the where we are, in what set we consider the integral. For that reason, the set is different, but the operator is the same. That is the principal difference between with the notation using by Boyer, for example. Boyer don't make the difference in the match over the integration, but he make a difference of the operator. For that reason, in his notation, he introduced the var and the tilde in order to consider the operator are be different depend of in what match you are using. Okay, here we have our integration by part. Well, with this, we are now the proof of the stability result is again using a Kahneman estimate. We developed this Kahneman estimate for the discrete semi-discrete system. This is very similar to the continuous case. The principal difference is here this red term, which is bounded for the parameter of the Kahneman. This Kahneman is with boundary term. We follow more or less the tools introduced by Boyer et al. And the new ingredient we compare with Boyer is we consider a function is not zero on the boundary. The other important issues in the proof is one of the main difficulty in the development of the discrete or semi-discrete Kalman estimate is to compute multiple discrete operators such D and average operator on the Kalman wave function. For this reason, we established this theorem to reduce some tedious computation, and it's represent an extension of the result presented by Boyer et al. In 2010 related to the discrete estimate on the weight function. Here R and rho represent the coefficient which appear when you try to compute the Kalman estimate. And this notation is very awful in some sense, but it's very nice, it's very simple to see how appear this principal operator, because the operator A, which is average, go to the identity. For that reason, when you try to go looking for what is his principal component, you see the operator I go to identity and the operator D go to the derivative. For that reason here, for example, appear the derivative respect to X, L times, and go the other terms. For the Poincaré, we have this result for the Poincaré. The Poincaré inequality with weight is this one in the discrete sense. The proof is very easy because here we take these terms and we consider this expression. Here we apply a Cauchy-Schwarz inequality, and then we apply a Fubini. Finally, we consider simple the function phi is decreasing. For that reason, the exponential of function phi is decreasing, and we can estimate in this form the expression. This proof is for any point in the mesh. For that reason, now we need integrate over the mesh or sum over the mesh, and we obtain the inequality. And with these two ingredients, the Kalman estimate for the semi-discrete and this estimate, we can compute the stability estimate for our problem, and with this we obtain our result of the unique continuation property for this equation. Finally, I want to present some work in progress. We want to extend the analysis for high dimension. We want to consider the previous analysis, but in the case where the Laplacian is taken in high dimension. And we want to consider a fully discrete system, maybe follow the ideas presented by Victor Santamaria in his paper. And of course, maybe try to include nonlinear terms in our analysis in order to consider the original BBM equation. Well, that was the presentation.
Well, thank you very much, Rodrigo.
Thank you, Rodrigo.
So there is time for questions, if you wish. Or if you wish to ask a question, please raise your hand. So you can do it on using Zoom or just turn on your camera and raise your hand. So, okay. In the meantime, maybe I'd like to ask a question. So here on the lower order terms, it seemed at some point that it was important to have something which is centered, right? The discretization on the terms in dx was UG plus 1 minus UG minus 1. Is it really important in your proof?
What?
So here, yes. After PI,
Yes.
You see the discretization in here is centered.
Yes. Yes. Actually,
is it really important?
Actually, from our analysis, is not so important the type of this discretization. But when we talk with the people related with the numerical analysis, they say when we consider a discretization, the idea is consider discretization of the same order. And here the Laplacian is the order h squared. And this is this discretization for the derivative is the order h squared. If you consider other discretization, for example, and the up discretization, or I don't know, maybe the order here is only h. For that reason, is from the numerical point of view, are be know very well or not compatible with the order of the Laplacian. For that reason, we consider this one, this discretization.
Okay. But otherwise, from the technical point of view, I would say it's probably the same, right?
Yes, yes. In some sense, yes. We need to absorb this term. The idea is to absorb with the Carleman terms. What is? Yes. The idea is to absorb these two terms with the other one. Then, if of course, would you consider other expression? Here, no, sorry. Yes, if you consider other expression, is if you can absorb, it is possible to obtain the same result.
Sorry, and can you explain maybe one more time what is VH in your? So you have some lemma with VH. So I think it's the one afterwards. Here, what is VH? I don't get it.
Yes, VH is a UT. We consider VH as UT.
UT.
Let me show you in the continuous case. It's more simple to explain in the continuous case. In the continuous case, yes. You have this one, and B, you take UT.
Okay.
Actually, this is very funny, at least for me, because you obtain a Carleman inequality for this evolution equation, but only consider a Carleman for the stationary problem for the Laplacian.
The Laplace operator. Okay. Well, thank you, Rodrigo. Is there any other question? You can also ask in the chat if you wish. Well, so if not, let's thank again Rodrigo. Thank you. And so we'll jump to Andrew. Andrew, please, can you share your screen and turn on your microphone as well? My screen is
all right.
black.
Should be able to see.
Yes.
And let me test the slide moved. Things working.
It seems to work. Yes.
Okay. Okay, great.
So let's go. So the next talk will be given by Walton Green. So on local and global estimates for holomorphic function. Well, thank you, Walton.
Thank you very much, Sylvain, and the other organizers. Very happy to be invited to give this talk here, and also thankful for their work in organizing this great seminar with lots of great speakers throughout the past year or so. Okay, so let me begin. So we're going to talk about, we're not going to actually ever see a PDE or a control problem or something here, but I'm going to talk about some ideas that can be applied in control theory, and that if you look at the papers that would talk about, there's the details and everything. But since everyone here is more or less expert in control theory, then I don't want to waste my time with those details, I want to get to something that maybe you've not seen before and that could be interesting to the audience. So the kind of abstract setup that we're going to look at is we want to think of some sort of domain, omega, a measure space, and we think of some sort of function space within there. So within the Lebesgue spaces on that domain. And then within the domain, omega, we want to look at subsets, E, which kind of contain all the information of F, of functions in F. So we want to look for subsets for which we have the continuous inequality. You may already be thinking this observability inequality, right? That all the information of F is contained on the set E. So, you know, we couldn't have this sort of inequality for if script F was the whole function space here, but rather we need some, you know, extra structure imposed on our functions, something like holomorphic, which is what we mentioned here, or some sort of Fourier decay. It's very common, and I mean, there's countless different types we could consider. And often of interest is also the constant here, which of course would depend on the set E in some way and depends on the function space F as well. And that constant we'll call the sampling constant. And it's important to get sharp estimates on this in many cases. And a more general problem is to look at, instead of looking at sets E here, we can look at measures nu for which these two norms are comparable. And so the above dominating set problem is taking nu to be a indicator function multiplied by the measure d mu. So this is the case above of the dominating set is a special case of this problem. So where do these inequalities connect to control theory? So let's go on to words that the terms that are probably more familiar, which are the spectral inequalities and uncertainty principles. So to apply such results to control theory, oftentimes we look at F, which is some spectral subspace of LP. So if we have self-joint operator on LP, or L2 in that case, so yeah, that should probably be L2. Then we look at the spectral subspace defined by some sort of spectral projection here. So I wasn't able, you know, to mention all the authors who have worked on problems of this type because this is a very abstract setup. So, you know, so many authors fall into this category. So I just wanted to mention sort of the pioneers. And when it comes to parabolic equations, the spectral inequality was pioneered by Lebeau and Robiano in their study of the heat equation. And that is their ideas, and new ideas also have been implemented for different types of parabolic equations. So I don't really mention anyone because it would be a whole slide by itself or multiple slides just listing the different authors who have worked in the parabolic case. And in the hyperbolic case, I think less has been done, and that's I tried to list a couple of other authors who have pioneered in the hyperbolic setting. And that's the one that I'm going to talk about. So included a couple other authors here. And in both cases, the importance is we have a parameter R. So we either consider a spectral interval, which is like a ball centered at 0, or which is like a small interval shifted all around the real line. And we want to track the dependence on the location of this interval or the width of this ball. And so now we'll come to the actual function space that we'll look at, which is called a Paley-Wiener space. And it's defined by the Fourier transform being supported. That's where how the spectral projection takes its form. And contained in this annulus. We use A for annulus, so it's you can draw a quick picture. The annulus has radius R, and then this little bit here is beta. So this width is beta. Okay, and then this, shade this in. This is the annulus that we're going to be looking at. And so we look at functions whose Fourier transform is supported here in the annulus. So the first result that we'll talk about is the setup we need is to talk about the geometric control condition. So there are many forms of this depending on your operator A, the form of your Laplacian, and the form of your domain, if it's a manifold or anything. But here we're thinking in the simple case of on the Euclidean space with the pure Laplacian. And in this case, the geometric control condition can be formulated like this, that if we take the Hausdorff one-dimensional measure of our set intersected with any line of a particular length, then that remains positive. So I didn't write this down, but H1 is a Hausdorff measure of dimension 1. So for such sets, we had the following uncertainty principle or spectral inequality, depending on the form you want to take it. It can also fit into what we introduced at the beginning of a dominating set for this Paley-Wiener space. So we fix a couple of parameters, L, gamma, beta, delta. And with those parameters fixed, there's a constant. So that's why constant only depends on those parameters. And then for any set E satisfying the geometric control condition and any R positive, we have the dominating set inequality. And notice that here we have replaced E with E delta, which means a delta neighborhood of E. And then this is for all F in the Paley-Wiener space, which you recall that means support F hat is contained in the annulus. So this is the one of the main results that I want to talk about, and emphasize that this does not depend on R. So there's one constant depending only on the parameters, and then any E which satisfies this geometric control condition, and any R positive, any radius of the annulus. Then for all functions in there, we have the continuous observability. And now we might want to wonder about the delta neighborhood. We'll see in the proof why it's needed. And however, when the dimension is 1, we can actually remove the delta neighborhood. And this comes from a similar result that's actually, in the one-dimensional case, it's already been proved, because in that case, the annulus is much simpler. We don't have to really consider this huge, but the annulus is getting larger as R gets larger, even though it's of fixed width. But in one dimension, that doesn't happen. We just have two intervals, and then they're sliding, further away from each other. So that result is already known, and so I was able to apply that to this problem of the wave and Klein-Gordon equation in this paper, and then I was inspired from that due to these works by Burke and Joly, where in neither of these works do they prove this theorem. So that's why I say related results. But as a consequence of this theorem, we get a result on the wave equation, which has to do with observability, and it also has to do with damped equation, the energy decay. And those problems are studied by Burke and Joly in this paper, in actually a much more general case than we're able to recover. They don't consider pure Laplacian. They don't consider, omega equals R. They're on a manifold, and so they have much more complete results as far as the wave equation itself goes. And then in this paper in these series of papers by Mali and Stanislavova, they do D equals 1, and we recovered their results using a different method. There's our, especially this first paper is very, very involved with the spectral analysis, and very nice, I mean, breakthrough paper, and we were able to recover their result and extend it to other values of D. All right, so let's speak for a second about this proof and how it relates to the title of the talk, which is local and global estimates for holomorphic functions. So the first step in the proof is a new characterization of the GCC sets. So we have this measure theoretic definition, but we can actually give a function theoretic characterization as well. So we first characterize the set satisfying GCC as those E for which we have this inequality whenever F hat is contained not in this annulus, but now we look at much simpler geometry, which is the strip. So what I mean by this is the strip, let's say 0 to beta, and then this is, let's say this is the axis, or D minus 1, this is the axis R, then we're in this sort of strip. So, and then we can rotate that strip around, translate it, and everything. And if we do all of that, if we consider all of those functions, then that will tell us that if we have this continuous, reconstruction for all of those functions, for all of those strips, then we know that our set E actually has to satisfy the geometric control condition. And so we'll come back to how to prove this at the end. But briefly, let's discuss how to get this result for the annulus from this result. So it's a simple argument using the decay of the Fourier transform. So we take our annulus, which is drawn for two different values of R, here and here. Let's do this, R small, R large. And you can see that as you increase the radius, the portion here contained in a strip, like here versus here, is increasing, right? The distance here from some centered point to the remaining part of the annulus is increasing. So that's where we use the basically decay. So we cut off our function around C0, and that's what we call G. So we do a smooth cutoff there, and then that will tell us that this portion actually is almost orthogonal to this portion because of the decay properties. So, and that's where we introduce the neighborhood delta, because we're smoothly cutting off this, and by the uncertainty principle, there has to be some trade-off there. So that's where we get the almost orthogonality. And so this is a formal statement of the almost orthogonality. And then we apply the known result on this portion. We apply star to get back to G of L2 of E. And then to get back to F, we have to pay the price of delta, because we've gone with the support of this cutoff might, it basically will fuzzy out. It will average out our function around there. Okay, so that's the idea using the Fourier decay. It really relies on the smoothness of the sphere. And that's the only real property that it turns out we have used. So we actually have a more general theorem, and it allowed us to introduce this new idea of the k-dimensional geometric control condition. So in the previous example, we had the annulus, which was a neighborhood of the spherical shell. So the sphere dilated by some r, and then we take a small neighborhood of that. And that's the sphere is a d-1 dimensional manifold, and the GCC tests over lines, which are one-dimensional. So we can already kind of see the dimension, codimension here. And that's we actually have a more general statement. So if we fix K in between 1 and D, then E satisfies the K GCC. if there exists. So now instead of testing over lines, we test over k-dimensional cubes, Q, and we still assume this remains positive uniformly. And then our result is that if we take any d minus k dimensional manifold, smooth, it needs to be a little bit smooth, but once we have that, then we have the dominating set property as long as supportive F is contained in some dilate of this manifold. So in the previous examples, sigma was the sphere, the d minus one dimensional sphere, but and then the neighborhood is the annulus. But now this, like a similar way, is if we look at a circle, then we are now looking at like this tube, like inner tube looking thing. So with that in mind, there's like this codimension analog of the previous result. Okay, so now let's get back to this this result. So how do we connect the GCC to this, what you may call uncertainty principle or spectral inequality or dominating set theorem for functions whose Fourier transform is supported in strip? So it relies on the following local estimate, which we'll pose as a question. So for given two constants, for what sets, so we're thinking of three sets. That's why we call this a three-sphere type inequality or Rumez inequality, but we can also call it a three-sphere inequality. And because usually these are all spheres, x, y, e, y, x. And but we want to now kind of destroy that rigid structure and see how far we can push the geometric properties. So to apply this to the previous theorem, we actually don't need a very general property. We can take x and y to be balls or spheres or cubes, something very Euclidean, and then take E to be any set of positive measure. So that's for the previous result, this is already, we don't need to push this x and y to any strange geometries. Nonetheless, we want to in the future. So some discussion historically on such types of inequalities is given here. Classically, this is something like the Hadamard theorem or Nevin-Linna's theorem on two constants. And many other authors have pushed this idea to other classes of functions for plurisubharmonic functions and E of positive measure. This was done by Bruni. And then many other authors have looked at when E and Y are in the real line and X is a complex neighborhood of Y. And that's actually the case that we use. And that's already been proved by many people have done different variations on that theme. And the most interesting one for us, and what we'll use to extend this, is the result of Lebeau and Moyano, which came out now over 2 years ago. And for them, they are able to actually kind of get it for different geometries, but for only one fixed different geometry. So we'll actually extend their ideas to get a kind of a real answer to this question that we've posed. And then we also have to mention a result of Loganov, Milenikova, where they do many amazing improvements on the known things beforehand. First of all, they can consider any function which is harmonic. And harmonic can mean solution to any elliptic PDE with certain parameters. And they can even take E to be a lower dimensional set. So this is an amazing result that they have done. They won the Clay Prize for this result, among other similar work. And this has already been kind of applied to control problems and spectral inequalities by Burke and another author who's I'm not 100% sure. I should have written this down. So I have to mention this amazing result of theirs. So now we want, but the trick about all of these is they actually require X and Y to have special geometry. Special, what do we mean by special? Usually that means they are Euclidean balls or cubes, or a certain neighborhood of an interval, or in the complex plane. So usually cubes or balls, Euclidean ones. Okay, so what we have done now is, in a slightly unrelated paper that doesn't have much to do with control theory, we were able to prove this idea. And what I want to do now is extend this and try and apply it to some similar problems in spectral inequalities and uncertainty principles. But for now, let's just state the result. So this was, I worked on this with a graduate student, Nathan Wagner, at WashU, and we were able to show that, so we fix a couple of parameters again, which you'll see their role in the future. But once we fix those parameters, then uniform over all sets satisfying the following geometric conditions, we have the local estimate here. And this A2, I didn't say what that is. So let's just say F holomorphic. That was an old slide. Okay. So now let's state the geometric conditions. They are that Y is not too thin or something, right? It's kind of ball-like in the sense that its measure is comparable to its diameter. And then the second condition is that there's some boundary separation between X and Y, which are, again, comparable to the diameter. But we could normalize, so diameter is 1, so we could think about this saying that the measure does not degenerate and the boundary separation does not degenerate over some family of X's and Y's. And then we can take any subset of Y with positive measure. And then we have the three-sphere inequality here, which says that values of the function on Y can be controlled by, it's like a unique continuation, right? Of course, if this is, that's not interesting for holomorphic functions because we already know if this is 0, then the whole function is 0. But it's a quantitative version of that. And now let's mention the proof in the last minute or so of the talk. So the proof, we use Carleman estimate, kind of the oldest version of Carleman estimate even, which is for the d-bar equation. So the analytic function satisfies the d-bar equation. And we use each component of the d-bar equation, and we obtain this Carleman estimate for any function here. And very conveniently, what arises as the weight is just the Laplacian of phi. So we want to pick now phi to be some solution of Poisson's equation satisfying some property. So we pick phi to satisfy this. So this will give us the values on E, and this will give us the values on Y, and then here we have the values on X. So the last thing to do is pick the parameters so that the exponential weights work as they're supposed to for the Carleman estimate, right? We actually need the weight to be smaller on X, near the boundary of X, than its infimum on Y. That's how the Carleman estimate usually works, right? So to do that, we have to pick our parameters. We have to pick rho small enough. So rho small enough allows this first part to happen, where the info over y is positive. But then at the boundary now, so this is the notation we use for like the neighborhood of the boundary. So, but near the boundary, it's small and smaller than like 1/2 of delta. So that will give us the correct exponential weights. And how do we do such a, how do we show that these properties really hold? Well, that's where we have to use these geometric assumptions. So what it relies on is some estimates for the green function. So phi is equal to g of xy times some function, if we call this chi oy dy, and where g is the green function for x. And then we need some uniform estimates for the green function depending only on these properties. So that's what we have to use there. So we use the fact that like the Green's function goes to 0 as y goes to the boundary. And then we also use the property that it remains positive away from the boundary. So let's say for y not in this set. And we hope that this happens uniformly over all of the x and y satisfying this condition, these conditions. And that does happen, but that's where we use the geometric conditions, is getting these green function estimates, which allow us to show that the weight that we choose, phi, actually behaves like this. But once we have that, then we can complete the Karlman estimate using standard tricks, right? So once we do that, then Laplace phi becomes indicator y, so bring that over here. And indicator e, so I bring that over here, and then indicator y is right here. And then we optimize, pick h appropriately so that the sum becomes a product. So that's the local estimate for holomorphic functions, and we have applied it in a simplified form previously to these uncertainty principles, spectral inequalities. But now what we want to do in the future is apply this in studying control theory in settings where the metric structure is not, where the right structure is not exactly Euclidean balls or cubes. And so that's actually where this arose. We were studying dominating sets for some Bergman space, which is a space of complex variables of holomorphic functions. But there, the correct metric was not the Euclidean metric, but some hyperbolic one. And so we needed this this different result. And so now I want to start looking at how to apply this result in control theory, possibly in some hyperbolic geometric setting. Okay, so that's a good place to stop. We're at the end, and I'd like to thank everyone for attending, and again thank the organizers for this great opportunity.
Well, thank you, Walton, for this very nice talk. So as usual, I'm uploading in the name of everyone, right? Are there any questions? If so, you can open your camera and raise your hand, or raise your hand on Zoom. Well, so in the meantime, if I may, I have a question, in fact, regarding the link with the wave equation.
Yes.
You said your geometric control condition. I did not clearly understand how it is related to the one which is known for the wave equation.
Okay, yes. So yeah, the usual one for the wave equation is that you take the Laplacian, whatever it looks like, the Hamiltonian, and then you look at its trajectories, its geodesics, and you require that those geodesics intersect your set with some positive measure. Or usually it's actually stated on some open set, but that's because usually the domain is compact and you're assuming your set is open. So positive measure or if your set is open, then yeah, positive measure is the same as non-empty open section, intersection. So for the Laplacian, those trajectories are just straight lines. And we're kind of dispensing with the regularity and replacing the open set with the positive measure.
Yeah. So yeah, I see that now. In fact, I haven't read before that it concerned lines of length L, which is, of course, like similar to the time in the context of the wave equation.
Oh, yes, that's a good point. Sure. Yeah.
Okay, so in principle,
L is like the time. Yeah, exactly.
So in principle, you could also interpret the results which are proved in the context of the wave equation as results in Palavinar classes, or not? I mean, you can do it in the other sense, no?
I have never thought about that. You could very well be right, but I've never checked. You said Nevin-Lina classes?
Well, I don't know. I just it just reminds me some works which have been done by Tuxnak, Tenenbaum, Ramdani, and Takahashi on spectral. It is called spectral wave packets in that work.
Yeah.
But the principle is very close to what you are saying here on considering functions which are supported in an analysis in Fourier. And so, yeah, I just wonder if there could be some other approach.
I'm sure that that's related. I mean, I do not know that exact paper, but I know those authors have worked on similar things.
Well, okay, thank you. Are there any other questions?
Thank you. Yes. Sorry.
Yes.
Okay. Just some kind of quantitative question. In the last inequality that you have shown, can you say something on theta? Can you say which is the dependence of theta? How does it look like?
Okay, so theta, I state that when I don't need to talk about the sampling constant, I state the result this way. But it's easier for me to think, so you divide through by L2 of y to the 1 minus theta. And this is the same as FL2y less than FL2e to the theta over 1 minus theta. And then times this ratio of F over F L2y, L2x to some power maybe. I don't know. But anyways, in this form, oh, no. Okay, yeah. Okay, so in this form, yeah, and then here goes, I'm sorry, yeah, here goes 1 minus theta over theta. Yes. So in this form, this is the kind of the relevant constant. And that is of the form, it's polynomial in, so then we usually write, call this n, or then we define n to be log of x over y of this quantity.
Okay.
And then in that case, all of this here becomes c over gamma to the c times n. Okay, so that's sorry, that was a lot of more work, but yes, the importance, and this is of interest, is that so this gamma is like the density, and it depends polynomially on the inverse of the density, not exponentially. So sometimes, yeah, this would be like c to the gamma in c, something like this. So that didn't exactly answer your question. I'm sorry about theta, but this is the, if you do the computations, and yeah, usually these results are actually stated like this, where you have L2y, L2e, and then you're interested in this doubling constant in.
Yeah. Okay. Thank you.
Thank you. Are there any other questions? Yves?
Yes. In other words, you claim that there is a concentration of F in the set E. Yes? It
Yes.
is to resume. Yeah. It is not a question.
Yes, it's about the, there's some positive amount of information on E that affects, everywhere. It's also, sometimes these results are called a propagation of smallness. For that reason, the smallness of E, if it's smallest at E, then that propagates to all of Y.
Okay.
Well, thank you. Are there any other questions? So if not, let's thank again Walton for this very, very nice talk. So it was the last session for this academic year, and well, probably we will start it again next year. We still don't know under which form, but okay, we'll see, and we'll keep you informed. And so in the meantime, happy holidays for those who have some, and see you soon.